So before we get into any of the rules, I want to talk a little bit about notation. And what do I mean by notation? I mean, how do we express a derivative, and how do we physically write down a derivative? So you've seen some notation already, but I'll give you some names for it that we might actually call it by. So Leibniz, I hope that's how it's pronounced, comes from the 17th and early 18th century, and his notation for a derivative was this fraction, d over dx, or dy dx, and just d dx is called like a derivative operator with respect to x. You're just, given an expression in terms of x, finding its derivative. That's d dx. But dy dx is finding the derivative of y with respect to x, and it's a fraction in terms of differentials, when dy and dx are differentials. So this is a differential. So Leibniz notation can be considered a fraction of two differentials, and we'll get into more of that in the coming videos. But this is the iconic calculus notation. If you want to take multiple derivatives for d dx, you do something like d squared over dx squared, or you can do d squared y over dx squared, and you can replace the 2 by any n. So that's Leibniz. There's also Lagrange notation, Lagrange, and he is that prime notation, y prime, y double prime, f prime of x, f double prime of x, or f n of x for any ordered derivative, or y to the n. Stuff like that. So this is self-explanatory, this is easy to understand, it's just y prime. And these are the two main notations that you'll see for single variable calculus. There's also Euler notation, and he liked putting capital D's before his f to indicate the first derivative, or n for any order derivative. And you don't see this as much, people don't really use this. Sometimes in Calc 3 classes for multivariable, this df stands for a matrix called the Jacobian matrix. But that's getting ahead of ourselves by a full year of math. It's cool. It's a matrix made up of all the possible partial derivatives, the first partial derivatives of a function. Now I want to talk about actual rules, and the first rule that we came up with was the power rule. And I don't think we've written a general case for it, but I will now, and that is going to be x to the n. How about, I'll write it like this, actually. So d dx of x to the n is going to be equal to, you bring the n to the coefficient of the x term, so it's going to be n times x, and then you decrement the power of this n by 1. You keep it up there, but you decrement it by 1. So it's going to be n times x to the n minus 1. So here are a couple examples. What is the derivative of x to the 7th power? Well, according to this, 7 is our exponent. We take it to the coefficient of the x, so it's going to be 7x, but we're missing this exponent, which we decrement by 1, so it's 7 minus 1, which is 6, and that is going to be our derivative. Another example, the derivative of 10x squared. So the derivative of 10x squared is going to be, well, the same. We take this exponent, we bring it to the coefficient of the x, but now we're multiplying it by 10 because the 10 was also next to the x. So if there's a constant as your coefficient, you're also going to multiply that coefficient by your exponent. So actually this is 10 times 2, or 20 times x, and we can actually leave it like that because 2 minus 1 is 1. So it's just x, so that is our derivative. How about the derivative of 5x? Well, we can think of this as 5x to the first power. We take the 1 and bring it to the coefficient of x, which isn't going to do anything. So that's just 5x, and then 1 minus 1 is 0. So this is 5x to the 0 power, which is just 5. So if you just have an x to the first power, the derivative is just going to be that coefficient. And what is the derivative of just a constant? Well, if you think about it on the coordinate plane, y equals 5 is just going to be a horizontal line, right? So if you draw the xy plane like this, y equals 5 is going to be like this. And it has a slope of 0. It has a slope of 0 because it's a horizontal line. So the derivative of any constant is going to be 0. So that was the power rule. Now I want to introduce you to the product rule. And the product rule is now dealing with the derivative of a first function times a second function. So we're dealing with a function f of x times a second function g of x. And to make notation easier, I'm going to make f of x equal to v. I'm going to make g of x equal to u. Actually, the other way around. I'm going to make f of x equal to u and g of x equal to v. And just note that u and v are not variables, they're functions in terms of x. So this product rule states, and I'm just going to state it right away, is that the derivative of u, the function f of x, times the function v, or g of x, is going to be equal to the derivative of the first function, so u prime, times the second function, plus, just the second function, not the derivative of the second function, plus the derivative of the second function times just the first function. Let's just do one example of the product rule. So I want to find the derivative of sine of x times 5x squared. So what is this going to be? Well, the derivative of sine of x, so if sine of x is our u, right, so it states that we have to find the derivative of u, which is cosine x, times just the second function, plus the derivative of the second function, which is 10x, times just the first function, which is sine of x. And so when we make this a bit neater, we get 5x squared cosine of x plus 10x sine of x. So that's our derivative. In general, it's useful to know this. The derivative of sine of x is equal to cosine of x, and the derivative of cosine x is equal to negative sine of x. So actually, wait, did I do this right? Yeah, I did do this right. I was worried that I missed a negative sign here, but no, I did it right. And the derivative of tangent of x, well, we'll get to that. Okay, so the last rule is the quotient rule. And it's very similar to the product rule, except now we're taking the derivative of the quotient of two functions, u divided by v. And this is going to be equal to v times u prime minus u times v prime, all of that over v squared. And again, u is f prime of x and v is g prime of x. They're two different functions. So let's do one example of the quotient rule. So d dx of sine of x over cosine x. Now you know why I didn't say the derivative of tan x, because sine of x over cosine x is just tan x. And we're actually going to use the quotient rule to derive what tangent of x is, the derivative of tangent of x is. So what do? We just follow this formula. So we get v, which is cosine of x, times u prime, which is also cosine x, minus u, which is sine of x, times v prime, which is negative sine of x. Why? Because cosine of x, the derivative of cosine x is negative sine x, and all of that over v squared, which is cosine of x squared. This is going to be equal to cosine squared x plus sine squared x, all of that over cosine squared x. And what is cosine squared x plus sine squared x? Well, that's just 1, right? The Pythagorean identity. So we get 1 over cosine squared x. And if you remember from your trig, 1 over cosine squared x is the same thing as secant squared of x. So the derivative of tangent of x is secant squared of x.